And then share screen. Share. And here you are. Okay, so make sure that this is in the middle so that you can go back.
That's right.
Good?
Yep. Wanna say anything?
No.
No, all yours. Well, we can continue. This is something that I really value and appreciate, so I'm probably spending a couple extra slides on it, just for that reason. And this is where I kind of showed you last time, where this is a chromatograph that happens to be a sample. These are, of course, it's one component or more. And so this would be typical chromatograph. We took the one little part of that chromatograph, which you probably can't see, and stretched it. We take a look and we see it here. Now, what we'll also do is that, notice we got the orange, that's what the machine draws. But under that orange, we have other peaks. And those other peaks are what are expanded here. Here's the orange. This orange peak is actually made up of one compound and a separate compound, two separate compounds. But they run so close together, they almost look symmetrical. I mean, that's one thing you always look at. Is a peak symmetrical? Does it look like there's a partial separation? And it looks actually pretty good. But in fact, the machine is sampling probably 50 times a second, maybe more than that. And so it's getting a list of all the ions, all the fragments that have been busted up in here. It starts saying, hey, one set of ions, one set of fragments is moving at a different rate. One set is moving faster than that set. It must be two compounds. So then it starts looking for what those two compounds might be. That's just another view of it. So this is then looking at the individual masses. Like you say, the machine is busting that up into masses, taking a tabulation of them, and lo and behold, it finds this set of masses, and this compound then gets identified down here as cyclohexane. So the 69 mass 111, we'll talk about mass spectrometry next. So you're doing a little backwards perhaps, but it says, okay, this set of ions, this set of fragments, I can find my library, this is what it is. Oh, and we got this other set over on this side, that's the 57 and 99 moving together, and that's 2,5-dimethyl heptane. So we're not separating that peak, by the machine, but the mass spectrometer is separating that into components. So, gas chromatography is probably second most powerful means of resolving compounds, mixtures of compounds. Capillary zone electrophoresis is the only technique that does better. So gas chromatography is tremendous for separation. And then you put mass spectrometry on it, it's really tremendous. So it's a tool that's made life much easier and certainly more certain. So, like I say, it's great at separation, but you need to know what you're doing too. So how can you improve separation? Because, when I said the number of flavor compounds, I hope I mentioned 11,300 compounds, flavor compounds been identified so far in nature. Well, can my machine separate 11,000? Probably not. But we certainly do our best. So again, we work at that. And how do we work with what parameters do we look at when we start saying, I want to do better than what I'm doing? This is our resolution over here. We want this peak or this number to be large. And this number is a function of three different components. One is the selectivity of your column coding inside, and the analytes you want to separate. If there's no affinity, if your analytes don't have any interaction with that column, there's no separation. So this kind of says, if I get the right column that likes the compounds I want to separate, there'll be an interaction, we'll do some separation. So making the right choice of column. The second one is kind of a thinky one in a sense. It's how early does this compound elute? If it elutes you make your injection and it's coming out, it didn't interact with anything on the way, I'm not going to get good separation. So this is kind of looking at the time of elution. So that's the time of elution. If K is very small, that one's important. That one down there makes this number really small. If K, long time in the column, this is lots of time for interaction between column, coding, and back, the mobile phase back and forth and back and forth. So again, we look at, can I stretch this out? Can I make this compound stay in that column longer? What can I do with that? And the last one is just a measurement. Does that peak broaden? I don't know if you've seen some peaks, but you've seen some pretty ugly ones where they come like this and they guys just go, not very interesting. I want them to go up, down, up, down. I want to have them sharp, nice sharp peaks. If they're very fat, they can overlap. I don't get resolution. I don't get them counted, my compounds counted. So we tend to work with the right column. We tend to look for conditions that leave that analyte in the column for some time. And we try to keep that peak broadening, that spreading of the column as little as possible. So how do we, or what measures do we have of separating power? There's typically a couple different measurements. Here, one is plates per meter, units of separation. And so efficiency measures plates per meter, we want this number large. And so we do things to make that large, and I'll talk about that. And the idea, kind of where this came from, plate, it's like a distillation. A single distillation does 1 unit separation. If I distill a sample 10 times, I'm getting more distillations. I'm getting bigger numbers. I can do a more efficient job. So it's kind of relates back to bench chemistry, not really this methodology. The other is HETP, height equivalent per theoretical plate. And that means how much of column, what length of column do I need to get a unit of separation? If it's really small, I get lots of separation, lots of distillations. And so this number I want small, this number I want big. So they kind of measure the same thing, but just a little different expression of that number. And I explain that because I'm going to show you two data in 2 different units, these 2 units. So factors influencing efficiency. Column phase, okay, what's my coding inside that column? And what's the column diameter? 2 very important. I assume you got to look at the column that was in the GC you were operating if you're in lab. It's a tiny, tiny column. The smaller the column, the more efficient it is. And that simply looks at flow through a column. If you got a pipe this big around, you're not going to have a nice uniform front of things moving through. It's going to be more or less shaped like a cone. But the smaller that diameter is, the smaller that cone, the smaller the separation of an analyte that goes through the column. And so we want small columns to give us efficiency. Here's kind of a range of column diameters that we use in chromatography today. The largest you see is 0.75 millimeters. That's a large column by today's standards. Our smallest column is typically around 0.1 millimeters. And so when we look at the relationship between column diameter and separating efficiency, here now, what do we want? We want the bigger number. What gives us the biggest unit separation? Small columns. The tinier the column, the more efficient. You might say then, well, gosh, why don't we then use tiny, 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 0.1 millimeters, kind of small already. But should we be working down here? Well, not really. Then they're so small, they don't handle your sample. It's just overloads the column and you don't get separation. So it's kind of an optimum that we work at. We can't really go down very well to the theoretical limit stuff. And so what we tend to do in our laboratory is we stay about 0.25 millimeters. So we could do better, but then it costs us in other ways. So here's where we go. You'll see sometimes work is done on 0.32 or 0.53, and you kind of wonder why. it's just not an efficient place to work. So small kind of columns, 0.25, 0.32, 0.25 is my favorite. This is where we want our number small. So the previous one, we wanted the number big. Here's where we got our number small. So how much column does it take to get a unit of separation? And so the smaller the units, the better, more efficient it is. So this relates to the column flow rate, column velocity. How fast is the gas? How fast is your mobile phase going through that column? Linear velocity, that should be centimeters per second, I believe. So centimeters per second flow through the column. And this plot is dependent upon what kind of mobile phase you have. Nitrogen could be a mobile phase, it's very inert gas. Helium could be, again, a nice column mobile phase, or it could be hydrogen. If we look at what's the most efficient, the lowest number, it's nitrogen. And you see some people using nitrogen to do their separations, their gas chromatography. It's cheap. It's clean enough, I guess, to do separations. But I kind of look at that and say, no, I would never use that. Why would I never use it? Well, I'm here at 10 centimeters per second flow through my column. My column is so slow, I'm gonna die of old age before I get this darn column, this peak out of here, this component out there. That's costing me money. And so if I use one of these other two gases, well, they're not quite as good. But look, I could maybe be doing 20 centimeters per second. Now my analysis time is cut in half. Maybe got here to 30, 40 to 50. A factor of 5, that's my retention time. I get my analysis done 2 times as fast or 5 times as quickly, whatever word I want to use. So, check that. That's nice if you're a theoretical chemist. But if you want to make money, if you want to do your job and get your work done, you push it out here. And very commonly, actually, in our laboratory, we change to hydrogen. And we're out here 70 to 80 centimeters per second. And that's troubling. So you get good data in the quickest time. Some people say hydrogen. Hydrogen's flammable, it's explosive. Do you worry about it in your gas chromatograph? No, not really. If you've ever tried to ignite hydrogen in the air, you have to have exactly the right composition. It isn't like you get a big leak and it blows up. There has to be not too much hydrogen. So it's actually tough in some cases to ignite, to say nothing about blowing up. So, if you're doing your job halfway, you're not going to blow anything up, probably even if you try. So we use hydrogen. Column, well, okay, phase thickness. There's a coating inside that column. And that coating can be varied by type of coating, it can be thickness of coating. The thicker the coating, the poorer the separation power. Why? You think about it. You've got your column, you have a coating on the inside, you've got your analyte moving through in this mobile phase. If that analyte just kind of contacts the edge of that coating, and then comes back out, okay, it's not there very long, it goes on its way. But another atom of your analyte, well, it doesn't only hit the surface, it decides it wants to go in. Uh-oh, the rest of my stuff's moving on. I've got some that are hanging below. I'm stretching out the elution. That peak is going from this, to something like that. And so thick coatings have some use. But again, you want to tend to keep them thin coatings to get the best efficiency. So thick phase, there's capacity. I can put lots of stuff on there, big sample on. You can deal with it. Thin phase has less capacity. I have to be fussier about how much I put on, how much sample I put in my insert. So this gives me separation. This gives me poor separation. But again, it depends upon whether you really want to put a lot of sample on for other reasons. Maybe you want to separate 2 compounds. And so I want to put enough material on that I can collect it and maybe inject it in something else. Well, then I'd probably go to thick phase because I can put a bigger sample, I get more to collect. If I just want to get a peak for measurement, I'm going to use a thin phase because I get my data quicker and more efficiently. Column length. The longer the column, the greater the separation. Okay, but again, it's another one of those things that if you have a long column, the column's twice as long. Most of our columns are 25 or 30 meters. That's kind of fairly decent length. But if I decide I want to get better separation, I really need better separation, and I get a 50-meter column, a 75-meter column, a 100-meter column, and all of a sudden it took me twice as long, 3 times as long, or 4 times to get my results. That doesn't interest me. I want to improve my separation by taking me longer. I want to improve my separation by doing it smarter in the sense of choosing your column, choosing your coating, choosing thickness, and so on. So long columns, they're used, but very, very seldom for exactly that reason. Every time you go to something longer, it takes you longer. So it's kind of what do you need? What's most important to you? Where do you want to sit in this pyramid? Is resolution, separation? I got a really tough separation. Well, then it kind of says, well, guess what? Capacity is not going to be very good. Sensitivity is not going to be very good. It's going to take me a long time. If I was interested in speed, it would be at the other parameters. So you always do some kind of a compromise. How can I compromise in terms of separating power, the time, the sensitivity, the capacity? So you work where you need to work. If resolution is not a problem, well, you push that sucker. You push it out for speed in that direction. So what do you need? And again, you think about that. So you just don't walk in and put a column in. You give the thoughts to all of these parameters and see which one gives you the best performance. We'll say a little bit about troubleshooting. And I think I started with you last time saying, read the manual, read the book, understand what the machine does and how it does it. And so that's extremely important to do. In terms of troubleshooting, though, if you're going to have a problem with your instrument, what's most likely? What's most likely to go wrong when you're doing gas chromatography? And this pretty well sets it up. Especially 80% of all problems are that you've got this gas flow, your mobile phase flow. It's not going the right place. It's not taking the right pathway. It's gotten, well, changed in one way or another. And I'll give you an example of that later to make a point. So actually plumbers, if you have a problem, a plumber is a good person to talk to because that's basically what you are. If you're in gas chromatography, you're plumbing a mobile phase to get it in the right place, the right time, and then go the right route to come out. So plumbing skills are very, very important. Approximately 10% is due to operator error. You screwed up, okay? 10% is actually due to hardware. So there's something went wrong with the instrument. And I'd probably bring that number down to 1% rather than 10. We have almost no problems with the hardware. Most of the time, it's something we've done, or like I say, something in the plumbing. What can you do about that 80% bracket? So does my gas go where I think it should be? Well, frequently analyze an instrument quality control sample and examine the data. Have some standard, a standard mixture. This is what I want to separate. I know there's not a problem with the sample. I know my sample. You put it on, does it work as it should? If it works as it should, okay, then life is good. The idea there is a difference between instrument QC sample and method. I'm just looking at the instrument. I want to put something known in to see if it gives me a response. If it gives me my response to my quality or quality control instrument quality. Anyway, if it gives me the separation, it's not the instrument, I messed up someplace. So I've done something wrong in methodology, something's entered I didn't expect. I think I mentioned this already. You're managing gas flows. You have to control the flow rates. You have to control the pressures in the system. And again, you do that carefully. Other 20% operator error oversight. frequent quality control samples. Again, randomize, put samples in that you know, have the instrument, the method, you go through the method with it, you go through the instrument with your quality control samples into interspace them within your analysis. So you know that everything is fine in terms of that. Hardware failures, like I say, that's really uncommon. Perform manufacturer's recommended preventive maintenance procedures, you bet. And again, there's so many new things on YouTube and videos these days. They can go in and find out how to change a column. You can figure out, okay, what happens if your septum leaks and how do you keep it from leaking? You can do maintenance. It's amazing all the things are in terms of YouTube. So do the maintenance. And sometimes that doesn't get done as it should. And it's amazing sometimes the things you find once you open up the system. You've got a nice rubber O-ring that makes a seal and you open it up and it's almost turned to dust because nobody bothered to look inside and check it out. So again, you do the maintenance on the machine. If you are going to have a maintenance, if there's a maintenance issue, you have to have somebody in. You do it by a trained professional, that's absolutely true. I don't suppose I can mention it, but all of my maintenance is done by a person that I give a little bonus at the end of each year. I won't tell you what kind of whiskey it is, but it works very well. He always comes and looks after us. He doesn't charge us, and he worked for the company for about 35 years, so he knows what he's doing. So let's look at where our leaks can happen. Where can our problems be? Well, you've seen this picture before. And so here's our gas cylinder over here. Our control valve is right here. We've got our pathway. Should it go that way? Should the gas go this way? And what routes do it take? So here's where our plumbing comes in. Does the right go here? Does the right go here? Does the right go in this direction? And so our problems are most commonly in this section of the gas chromatograph. There's a septum up on top. That's a polymer septum. Again, you're piercing that with a syringe, pierces it. You don't replace that fairly often. Guess what? You're going to have a hole up there. And guess where your flow is going to go? Your flow is going to come in and go that way. That doesn't help you with separation. So one choice, replace that septum. Replace it routinely. There's a seal up here. This is glass. That glass attaches to an aluminum block. How do you attach a glass piece to an aluminum block and not have it leak? Okay, there's a nice little seal in here, the septum seal. Again, a polymer. If that isn't changed, your gas flow comes down here and goes out around this direction. So again, you check the seal there. You check the seal up in this part of the instrument. So at the bottom is a graphite seal. So we've got our tiny column here, 0.25, 0.32 millimeter column coming in here. That has to be sealed across the bottom here. That's a graphite ferrule. So it's graphite. And again, you don't over tighten these things. And so you'll find most of your problems are here that I've mentioned, these three places. On some occasions, we have a problem out on this end. Maybe this valve hasn't been looked after, maybe it's been abused, so we cranked it too tightly. And so we can mess up our outlet flow by not having the right restriction here. So kind of 1, 2, 3, 4 places primarily that we look for leaks. We look for problems in gas flow. Oh, there's a mention of purge line. I guess that's an addition on here. Here we go. That shouldn't be plugged. There's been occasions when it has been plugged. So again, another place, you make sure the gas is coming out as it should. GC applications. So you're doing fatty acids. And I think that's the only one product you're doing about GSC, isn't it? Fatty acid profiles, good. So other than a headspace method, by headspace method, I mean, you take your sample, you put it in a closed container, you have a septum on the sample. You allow that sample, whatever you want, volatile compounds to come to equilibrium. You put a syringe down through it, drop some of the gas above your sample, go into a gas chromatograph, headspace sample. Very, very simple sampling. We do that sometimes looking for oxidation in foods. Oxidized foods have, again, compounds formed. They're very volatile. They'll go into the headspace, and you can measure in this way. But if it isn't a simple headspace or some kind of direct injection, then there are times when we make a direct injection too. I may be looking at orange oil. Beautiful flavoring material. There's 100, 200 components. And I can just take a tiny bit of that to inject the gas chromatograph. But most of the time, you're going through some kind of a sample preparation. And you did that for the fatty acids, even when you had pure fat. You had to put that sample in a form that you could do chromatography. So you weren't necessarily purifying the fat, but you're going through a chemical reaction to take the triglyceride and break it down into fatty acids so you can look at the fatty acid composition. So there's always some kind of a preparation, or most of the time I should say, some kind of a sample preparation that has to be looked after. So again, for sample preparation, one approach is, as I said, it's called a static headspace. It's a static system. There's no concentration that goes on. You simply have your closed bottle and you can just pull some sample out and inject it. But there are also some ways that you can concentrate that gas that's in the bottle. And so we have a couple different techniques. It's solid phase micro extraction. And so when we have something that we call a twister, so they're trade names. So we can give an example of how we concentrate that headspace to get better sensitivity. There's also, so this is static, the headspace is just at equilibrium, you don't mess with it. Dynamic headspace is you have your sample, and you may be passing a gas through that sample, bubble through that sample, so we have dynamic, a flow through your sample. That sample will come out, so we've purged. We're putting volatiles into that gas stream, they get concentrated here. So it's a concentration technique, dynamic headspace with an absorbent. So all of your headspace gases get concentrated by this absorbent. And there's a method called 10x absorbent, the solid phase micro extraction that goes along as well. So there are ways to deal with vapor phase methodologies. You analyze them directly or concentrate those samples. If it's a liquid injection, we can just simply use a syringe. That's pretty easy. It's typically a 10 microliter syringe. 10 microliters is a large amount of sample to put in an instrument. Probably only use normally 1 microliter. So you got 10 microliter syringe, but you drop 1. Fairly easy to do, easy to handle, they're kind of durable. So you put in 1 microliter, you chuck 99% of it, and you analyze what goes into the instrument. So what's a syringe injection? And there are solid methodologies as well. So you can heat your solid and give off compounds that you want to measure. So we'll go through some of these methodologies. Most common today, and I guess I'll comment on that, but were you shown any other tools or other ways to do sampling in lab? No? Okay. Well, this is called solid phase micro extraction. In my business, probably 80% of all published work is done using this technique. It's a crummy method. It really is. It lacks efficiency, poor separation, poor resolution, but it's easy. And so what do people do? They say, oh, we'll do it the easy way. Besides, look at everybody else that's using it. Why don't I like it? Well, I'll get to that. Because the way this is kind of an interesting form of a syringe. So we got a plunger, we got a way to kind of lock the plunger down and pull the plunger out. That goes down here onto a needle, and that needle is normally in the sheath. But okay, we can have it retracted in the sheath, or we can put it down so it's in the headspace above a sample, the gas above a sample, or we can actually put it into the product itself. if it's a liquid solution. You could put this down into a liquid solution, provided it didn't contaminate your syringe. So it's fairly simple that way. And like I say, that's why it's used so much. But I don't like it because, first of all, this fiber, it has very little ability to absorb compounds. There's differing affinity for different compounds. And so if you put this above a sample, well, what you see is going to depend upon what of your sample goes into the gas, and then what likes this. If your volatiles really don't like that coating, they have no solubility in that coating, forget it, you're not going to see them. Those that like it the best are going to be concentrated here. So your sample doesn't represent what your product is. And that's, like I say, a problem that people just kind of ignore because it's so easy. They talk about there's no solvent, no disposal, no contamination. In my opinion, no results. What's an alternative to this? Another methodology suffers from a little bit the same problems, but not so much. And so it is fairly to use. This is a glass, like a stir bar. It's kind of a small stir bar. It's kind of that idea. And so there's a magnet inside of it. And polydimethyl siloxane is basically the coating that's put on here. So it's got a coating on the stir bar. And you might be looking at something like a beverage. Okay, let's take the beverage. Let's drop this nice little coating here and mix in the beverage for a while. Use a magnet, take it off, dry it out, and take it and put it into your injection port. It's really hot and cheesy. Thoroughly dissolve everything off it and analyze it. And so it works really quite well for that. It's much more sensitive than your speening methodology. Speening has got a tiny little needle with some coating on it. This has a ton of coating, relatively speaking. And so you can get much more sample and better sampling representation. And it's still very easy to use. You drop it in, you pull it out. You can, for that matter, toss it into a jar that's got some flour in it. You can let it sit in there with the flour and absorb off flavors from the flour, if it was oxidizing, whatever. So it's really much more sensitive, easy to use. One problem you have is there's only one coating, polydimethyl siloxane. Speening has many different coatings. This is only one, and you hope it's good enough to absorb the compounds you want. It's the right material for that. But only one matrix, only one coating. It would be ideal if we had 3, 4, 5 different types of material to absorb different types of compounds. Fat loves it. Now you're in trouble. If you got fat in your sample, it's going to also go to that coating. When you drop it in your GC, 250 degrees centigrade, you burn the fat off, get it into your column, and have an absolute mess. So, okay, bad idea. You can cryofocus this. So when you put this into, when there's a machine for this, you can put this into a machine that heats it up and passes gas. So you can then take that gas and put it into a cryofocusing unit. So you concentrate everything here, so you can have focused at a spot here, then almost instantly heat that to drive it off into your gas chromatograph. If you don't visualize that, come down one day and I'll give you a tour. How's that? Tour of equipment. Applications of gas chromatography. There's certainly many of them. Biotechnology and flavor production, fermentation of oleic acid by microorganisms, chiral composition of flavor compounds. You can just go on and on for the different methodologies. In terms of some examples, culture medium, so you're growing a culture, you're extracting the culture of diethyl ether. Diethyl ether, very volatile, good solvent. So we extract what we want out of that culture. Flavor, we may be fermenting to produce a flavor compound. So I want to then extract that flavor compound and measure how much is formed by this microorganism. Take my ether, maybe 5 separate extractions, 40 mils each time. So I have 5 separate fractions with clean fresh solvent. Concentrate it down to 0.2 mils. So I go from 200 mils down to 0.2 mils. You may fractionate it. You could actually put that onto just a glass column and do some separation, further separation. Usually you don't have to. In this example, they did do a separation, so they concentrated, did a column chromatography, and then chromatographed each fraction of it. So doing GC analysis on the final product works very nicely. This is a separation that's based on that procedure. And it's looking at the chiral composition of delta decalactone. Delta decalactone, that's a beautiful compound. It's just very characteristic of coconut, heated butter, caramel, those kinds of characters. But what you need to know is if you're doing this by fermentation, and they do produce this particular flavor compound by fermentation, and then use it for, like, say, anything coconut and so on down the line, you have to know what you produce. And so again, by this methodology, the gas chromatograph will give you the chiral compound you want, is it the R or the S form, and separates on basic chirality in the process. So a beautiful method for quality assurance for fermentation to produce a flavor compound, a natural flavor compound. Residual diphenylamine on apples. Diphenylamine is used to treat apples, to control apple scald. So okay, it's fairly commonly used. There are limitations for residue on fresh apples. And so basically, the apples are dipped in the solution of diphenylamine. It's about 1 gram of diphenylamine, kilogram of solution. They're concerned about the residue on the apple. FDA permits 10 parts per million in the US. Some countries have absolutely no tolerance for it. So how are we going to analyze this? How are we going to tell whether or not we're meeting the FDA requirements? I love this one. What do? You put the apple in the solvent, swish it around. You take this, hexane. You concentrate it for the gas chromatograph, and they just put it under a gentle stream of nitrogen. So we got nitrogen gas coming down the surface. You got a beaker with your solvent, extraction solvent, and just simply let it concentrate. So it's concentrate enough so you can analyze it and make an injection into the GCMS. This is the gas chromatogram that comes from the surface of your apple. So there's not only one compound in there, there's a lot of things on the surface of your apple. Some of them belong and some of them, well, maybe they don't belong. So you get a gas chromatogram like that and you kind of say, okay, where's my compound? I want diphenylamine. Well, that's where mass spectrometry comes in. Diphenylamine is a major ion fragment. Diphenylamine gets hit by electrons and the mass spectrometer blows it into pieces. These are the pieces diphenylamine gets blown into. The mass spectrometer can go ahead and search and say, 169, that's the largest. I will key on 169 and look for compounds that are in that big run that have a mass of 169, fragment 169. And this is then going ahead and showing, here's you got a spike sample. Oops, that's this. I'll get the right one here. So we got some internal standard as we go along. And then we find this is our sample from our apple. This is our sample from the apple that's had a spike of a pure compound. A little bit of diphenylamine was added to it. So this comes from what was residue on the apple. This is when we fortified that. So we just make sure that didn't peak yet. Well, okay, we get same chromatography. And by mass spectrometry, we see the right peak showing up in both. So very, very simple procedure. That's one of the easiest. Fatty acid profile. So, okay, we're interested in determining a fatty acid profile for all kinds of reasons. Is the product going to oxidize and highly unsaturated? Is it going to be a shelf life problem? Is it going to be a liquid or a solid fat? You know, that saturation determines the phase or the form of the fat. Is it oil or a fat? Label requirements and so on. There's all kinds of reasons why we're interested in the fatty acid composition of a sample. And we have to start out by isolating pure fat from the food. So we got to separate that fat. away from the food before we can do gas chromatography. And that's, I don't know how you did it. You do it by a solvent extraction. Okay, so you solvent extracted the food. So you end up with a solvent, your fat in an organic solvent. Then you probably followed something along these lines. Boron trifluoride used for forming an ester. We can run lipids. We can actually run triglycerides, the intact triglyceride with the fatty acid. We wouldn't necessarily have to break it into pieces, but it's much more efficient and it gives more information. If we take that fat and break it into free fatty acids and measure the free fatty acids, not the triglyceride. And so that's what we do at this point. We can take 2 drops of fat, for example, put it into 3 mils of boron trifluoride, 20 mil test tube. That boron trifluoride transesterifies. It basically converts your free fatty acids away from the triglyceride and makes an ester of them. The ester of the fat is very volatile and runs very nicely. So you're freeing the fatty acids by the reagent and you're making a volatile derivative that's easy to measure. Put the tube in a boiling water bath for 1 hour, cool, add 3 mils of distilled water, add 10 mils of hexane. So we put water in, we're going to put hexane in. Your free fatty acids now, they're free at this point, they're off the triglyceride. They're going to be soluble in hexane. Take that top layer, and you may concentrate that down, and then maybe 1 mil, and inject it into the gas chromatograph. So you probably followed something like that for your methodology. Is there a change? Is what? Okay. And so that's a really simple methodology, very accurate methodology. Like I say, you've got to separate the fat from the food first, so you get working with pure fat, and then you can run through this methodology. And now your TA probably went ahead and gave you a standard. So he or she took some fatty acids, made esters of them, and put this mixture on a gas chromatograph. And so this is what a standard run should look like. So this is when you take pure compounds and run them through the system. So you have, I would think that's going to be C4, yeah. So that's butyric acid. It's the ethyl ester of butyric acid. This is, so that's C4, this is C6, caprylic, capric. And so we get the 4, 6, 8, 10, 12, 14, 16, 18 carbon, and then we've got 16 carbons with a double bond, but 18 carbons with a double bond, 2 double bonds or more. And out there, we can probably be running with the C20, but we find a listing here. So it's a nice run. So these are the times. So at this time, butyric acid is always going to come out. That's going to come out in 1.769 minutes. 90% of the time, it might be 1,000th of a minute faster, 1,000th of a minute slower, but whatever comes off, whatever fatty acid comes off at that point, that's butyric, that's caproic, that's and so on. So based on retention time of pure standards, you can then look at your sample. What does your sample have? And so vegetable oil, do you find any C4, 6, 8, 10, 12 in vegetables? Not really. And so if this would be a vegetable oil, we really don't find any of the 4, 6, 8, 10, 12, 14. What do we find? We've got palmitic acid, C16, and then we got 18 with some 1, 2, or 3 double bonds out here. So some of you will have chromatograms that look like this. Nothing up front, but then we got fatty acids down here. Wait, C16, 18, stearic acid, 18, 1 double bond, 2 double bonds. So based on retention time, you know what your fatty acid is. This is just another example looking at just the internal standards. So these are our pure compounds. And here then, probably just a blow up of the previous one. Here we see, okay, these retention times will always correspond to those fatty acid standards. Again, the next one goes ahead and shows you the retention time for each of those. There is a percent composition that's based on area. The area under the peak is proportional to the concentration of compound. So it's area under the peak. And your machine will give you a number of the total area. So the machine says, okay, you have 1, 2, 3, 4 peaks. Shouldn't be counting that one. So you have it set up so your machine counts only these that are fatty acids. It should add this area together and then divide it, your compound, by the total area. So it gives you percent composition of each of these fatty acids in that manner. And that isn't exactly correct, but it's really, really close. We call it typically close enough. Why isn't it exact? Well, not all compounds give you exactly the same response. So butyric acid, that first one, it has quite a bit of oxygen in it for the hydrocarbon. So it gives you a slightly different response than something with 20 carbon chain, where you've got still one oxygen group, and then the rest of it's hydrocarbon. So we typically don't make a correction for this. I don't think you do you, Bram? No. And you kind of assume that they all respond about the same, and that's close enough for most purposes. There's other cases where you may be measuring very different compounds, and you really can't get by with saying, oh, we'll just count the area percent. Because some things you get a poor response, some things you get a really good response. So you have to be aware of that. In this case, you're in good shape. Oh, darn, we ran out of slides. It's not bad though. Anyway, I think we'll probably. What time do we go to? What time do we go to? I thought you said 1:40. Okay.
I was to scare the kids.
I was because you scared me.
I was wondering, so in your procedure, you added water, but we were talking about esterifying